and welcome everyone to today's presentation, Getting Started with NASTRAN. We've kind of geared this at an introductory type of webinar. It's intended mainly for individuals who've either never seen NASTRAN or FEA before, or those that have a minimal exposure to it, just to kind of find out what the process is and what it can do and how it can help you. Quick overview about Hagerman. We are scattered across the U.S. coast to coast. We've got offices and locations and staff everywhere, especially now with the structure of how industry has moved to be more remote. We've got more coverage area and more people in more states to cover locations and do a lot of remote consulting, remote training. We still do occasionally go out for on-site when something like that is insisted upon and allowed based on current conditions. With our field technical staff, we are field experienced. We've been out there in the trenches with you guys. We've got over 175 years of combined experience, and that's just on the mechanical side. That's not even adding in the architectural side and the media side of our tech staff. We've also got over 30 years of software implementation experience for your CAD software, for your data management products, and various data management products that we specialize in. So let's start off with the big questions. What can NASTRAN do? We're not going to have a bunch of slides to go through. I'm going to get to the actual software demonstration as quickly as I can, but I at least want to expose everybody to where you have abilities to go, what you can analyze and what you can do and what you can get out of it. Now, there's a wide spectrum of what NASTRAN can do, and it's more than what is shown on this slide. Starting with the basics, you're looking at something like linear statics. We can also do buckling, modal analysis, pre-stress for static and normal modes. We've got composite material analysis capabilities. We've got assembly modeling with contacts. The big hit with assembly modeling and contacts is that enforced stress that comes from another component. A lot of times we don't even think about that when we're just thinking about the piece part level. We don't realize how much stress from another component could be impacting our design. And that can be critical to find if that design is going to work or fail. We also have thermal stress, and this is where a lot of red flags go up and a lot of questions get asked. And okay, what are we talking about when we get into a thermal situation? There are limitations for what NASTRAN has as far as thermal activity goes, but the thermal stress it can do is whether a temperature, high or low, is impacting the strength or inflicting a stress on your material and on your design. Then we get into things like nonlinear statics for not just nonlinear materials, but also nonlinear loading situations. It's no longer a static loading situation. It's now a dynamic load that changes over a duration of time. We get into that transient analysis when that comes up. Various options for linear steady state heat transfer. We've got drop and impact analysis that we can do as well. So let's talk about what NASTRAN cannot do or is not intended for. The big thing that comes up is any kind of temperature flow, whether that's temperature in a fluid or temperature in a gas. NASTRAN cannot analyze that movement of the temperature and that change of the temperature or the mixture of the temperature. Think of a kitchen water faucet, hot water, cold water. How does that water mix? That's not what NASTRAN is intended for. For things like that, you're looking at something like Simulations CFD, the computational fluid dynamics product from Autodesk. The other thing NASTRAN is not meant for is any kind of turbulence analysis. Again, that's where Sim CFD comes into play. Also, large-scale detailed structural analysis. In that situation, we do have the ability in NASTRAN to do frame analysis, line and beam element analysis on a structure. But when you get into something like a 20-story building or a large footprint of a building with 30,000 square feet on the first floor, that's a bit much for mechanical side to attack. So typically those models are created in something like Revit or AutoCAD architecture, and Autodesk has robot structural analysis for that side. So where NASTRAN is for the mechanical applications, robot is for the architectural applications. And then any kind of material liquefaction. Looking at the center model there on the screenshot, the hand controller for a gaming console, that's done with mold flow fluid analysis for plastic injection molding. So those are just kind of top level what NASTRAN is not meant to do. Real quick, let's just kind of eyeball the process here for FEA. You're going to have your model geometry created, or you're going to create it. That's step one. Step two is getting your material properties assigned. Now, this is probably one of the biggest things you've got to get right, because even a minor change in material properties can equate down the line to a large change in the results. And many times when we get callbacks from customers that, hey, the results don't match the shop, the first question I'll ask is, okay, does your computer material match your shop material? Well, we think so. Okay, you need to know so. So that's where you need to involve an outside lab, analyze your current material, find out what the calculated Poisson's ratio and Young's modulus and densities and things are of that material, and then plug that into the software. If you don't get that right, nothing else is going to be right. Then you step on to the next process. That's creating your mesh, or your net, as a lot of people call it. The mesh can really help you identify and zero in on where a problem might be. A mesh that's too generic or too coarse won't necessarily show enough detail for you to say, okay, the problem is in this confined area. It might be too widespread. For that matter, it could even be calculated in another location. So you have to refine your mesh, tweak it down, get smaller meshes, and even do local mesh control to zero in on exactly where that problem might be. Next, you're going to apply your loads and constraints. So what kind of constraints are we talking about here? What kind of operational conditions are we dealing with? How is this face held in place? Is it welded? Is it bolted? Is another piece holding that in place? So that's where you've got assemblies with contacts. And what kind of loading situation? Are you applying a load on one direction versus another direction, or has it got a multi-directional load vector? Get into those situations. Once all of that is set up properly, you run your analysis and you review results. This is probably a big question mark for most people. Is great, we've got results, but what do they mean? So we're going to look at that a little bit closer too. With the way FEA software works, it breaks down your model into a series of elements, and based on what kind of element we're going to deal with determines what result element you look at. For a solid model, we're typically working with some type of tetrahedron shape, a three-dimensional pyramid type shape. If you look at a surface model, that's classified as a shell element. With shell elements, they are planar surfaces, 3 to 4 points. I think 7 points is the max, if I remember correctly. Then you've got also a simplified version for cross-sectional analysis and beam analysis and structural analysis. That's dealing with a line element. So if you are building, let's say, a very small 2-story building, and you want to run some analysis on the beams, make sure they're carrying the proper load and not overstressed, you can take those beams and simplify them down into a line element to improve the analysis time. So let's jump into the demo. So let's talk about the basics of NASTRAN. NASTRAN runs inside of Inventor. You never leave Inventor to launch the software, to access any of the settings or any of that. Once NASTRAN is installed, it is located under the Environments ribbon tab of Inventor. You'll see here I have an Autodesk Inventor NASTRAN icon. When I launch that, it takes me into a sub-environment within Inventor. Again, I never leave the software. The advantage of this is not only the familiar interface, but if I need to make a geometry change the size of a fillet, the size of a hole, or a web material thickness. It's real easy to get out of NASTRAN, go back to the model, make that change, and come back in. There's no translation, there's no importing, there's no way to get this data kind of corrupted as it comes across. So the basic layout for NASTRAN, you essentially start at the left and move to the right, very similar to reading a book. We're over here on a default analysis. It starts out with a linear static by default. Every analysis starts that way. But if we need to change that, we can. When I edit the analysis type, I have access to all of these different types of analyses I can run. Default is linear static. You've got modal analysis, buckling, nonlinear analyses, transient response analyses. Once you change to some of these other types of analyses, some of the options of that analysis might change. So if I look at a nonlinear static, for example, I can change my nodal control, my output sets, look at the options, what kind of default contact I might be dealing with on an assembly setup, as well as looking at large displacements. So any type of material movement that is excessive would be classified as a nonlinear setup because that material movement is quite large. A linear static assumes the material is not going to move very much. So running with the linear static, the next step, moving to the right, is going to be setting up the materials. Now, if you have a material assigned in Inventor, that material will come over automatically into NASTRAN. Most of the time, we think of material kind of towards the end of the design process, so it may not be assigned, which is perfectly fine. In here, we can set up the material. We can pull from the existing Autodesk or the existing Inventor libraries, or for that matter, even a custom library. It is more productive and more efficient to have a material predefined. Just saves time if you're going to be using this material a lot. Let's say you have a material of ductile iron or a specific grade of gray iron. Go ahead and have that material assigned to one of your libraries with all of the appropriate controls. You won't have to define it on the fly every time. So for example, on this cast lever, if I'm going to analyze this as aluminum, when I choose aluminum from the Autodesk material library, many of the properties in here auto-populate, from modulus of elasticity to Poisson's ratio. Again, all of this can be assigned manually to a custom material when you create one, and it saves time going forward. If you don't assign that ahead of time and you just come in and start plugging in these numbers, there's a chance you could type the numbers wrong, and that can severely skew your results. So assigning it ahead of time in the library is definitely an advantage. So I am going to assign this particular material to that idealization. We've got our solid listed here. So I can come in and change that and say, well, let's make it a solid element, and it's going to be the aluminum 1100. And I'm just going to recolorize the mesh once I get to that point. At this point, you're choosing what type of element you're working with. In this case, it's a solid element, but I can also say, well, we're going to be working with some surfaces that might also be part of this model, or some structural shapes that may also be part of this model. You are not limited to working on one element type per analysis. An analysis can have all three. You can have some pieces that are solids, some that are shells, and some that are lines. Getting a pretty complicated analysis at that point, but it will work. If I switch over to a shell element, for example, again, you have access to adjust the material as well as define a global thickness. So this comes up a lot when you're working with sheet metal type of designs. You can also work with laminated materials as well, defining a new laminate structure, what that structure is, and what each layer is. So that gets down the path of working with composite materials. If I look at the line element options, again, you have material control there, as well as property input. So are we working with a structural member that came from the content center? The software will automatically simplify it if that's the case. If it's a custom cross-section, you can define that here with whatever your cross-section may be based on the different geometric shapes, T-shape, I-beam, cross-shape, bar stock, and you plug in your values. You can also be very detailed to input all of the properties manually on the fly. So I'll switch back to a solid element. It is going to assign the aluminum material to this particular casting. The next step in the tree is to work with any possible connectors that you may be working with. Connectors can take the place of other pieces of model geometry. So typically you don't model and analyze bolts and nuts and connecting rods like that. In most cases, we already know what the structural limitations of a lot of those types of fasteners is. So we don't waste the time to model that into the analysis. Plus, it takes more math, and it can slightly shift the results a little bit, taking into account some of that more detailed geometry. What we can do, however, is we can apply a simplified representation of that connector with a connector utility. It can be a rod connector, a cable, spring, a rigid body, or even a bolted connector. And what this does is it builds a graphical representation without putting any model geometry in there that needs to be analyzed. And connectors do function as constraints. You also have the ability to do offset surfaces in case you're working with sheet metal, to do mid-plane surfaces, or to take a solid model and simplify it down to a shell element surface model. And again, structural member definition if you need to do that. So the next thing we're going to process is the constraints. Constraints, you've got to get them right. And more than likely, the first time you apply them, they're not going to be right. You may think this is constrained in a particular fashion, and it may not be. Apply the constraints as best as you can understand how this part is being held in real life. What sort of braces are up against it? What sort of connecting rods or structures is it tied into? So for something like this, maybe I'm going to apply a fixed constraint to the main center shaft this crank arm is resting on. And you've got controls to whether you fully constrain it, if it's a fixed, to basically lock it down, it doesn't move, it doesn't go anywhere. Or does it have no translation, which means it cannot move in X, Y, or Z, but it can still rotate around those axes. Then you also have no rotation. So when I switch to no rotation, then it locks down the rotation around those axes, but it allows movement along X, Y, and Z. So this particular surface could slide along the X, Y, or Z directions, but it can't spin around them. Then you can, of course, open it up to be a free condition. There is no constraint limitation at all. For this particular situation, I'm going to apply a fixed constraint. Then you have some optional controls. It allows you to graphically represent where that constraint is, and you can adjust the size of the graphics. This does not indicate the level of control. We get that question a lot of time is, does that arrow mean it's more fixed than this? No, the arrow is simply a graphic to let you know here's where the constraint is, and depending on how large your model may be, you can adjust the size and the density just to make it more easily seen. But they do not indicate the level of constraining or the level of force, which is what we're going to get into next. You can also work with symmetry conditions. With symmetry, it can simplify on a very complex model. It can simplify the math, and the analysis time can be shortened down. If it is a symmetric model and it is encountering forces and constraints symmetrically, then analyzing one half of it will be a good indicator of what's going on in the overall. So go ahead and apply that constraint. Then we're going to apply two loading conditions. For this example, we're going to be loading the top two bolt holes of the fork, or the top spear, and we're going to apply 200 pounds in the negative Y direction. So that's what determines not just the amount, but how that loading is applied. So in this case, in the force and the Y direction, I'll just apply it negative 200. Changing my force arrows and colors, again, personal preference, and the size of the arrow and density of the arrow has nothing to do with the amount being applied. With this one, there is a little bit of a gotcha. Because I selected two different surfaces, I have to figure out how am I applying that load? Is that 200 pounds per surface, or is it 200 pounds total loading situation? And in this case, because I selected more than one surface, I do get the option to tell it this is a total force. So essentially, it's putting 100 pounds on each one of those top spheres. Go ahead and apply that loading condition. I'll create a second loading condition for the bottom two holes of the bottom fork. Same conditions apply, selecting both of the internal bolt holes and specifying the force and the direction. So this one is going to be 100 pounds in negative X. So that's why I put the negative in there, and specify total force situation. Lastly, change my arrows just for clarification of where that loading condition is. Okay, so I've got the constraints, I've got the material, I've got the constraints, I've got the loads, I've got everything checked. This is a single piece part, so I don't have to worry about any kind of assembly contact going on here. The other thing I might need to do is mesh it, but I think what I'm going to do first, just so I can really lock this in, is I'm going to come back and I'm going to apply a rigid body connector on that main central shaft, and I'm going to lock down that work point. So that's going to lock that. Even though I put a constraint on there for the cylinder, it's actually going to lock the outer faces in conjunction with that cylinder. So it's going to make sure it doesn't twist and doesn't move, because doing so might skew my results. So now we're ready to look at the actual mesh. So this is where a lot of people call it the net. You're going to throw the net, see what you can catch with it. The mesh has a lot of flexibility. If you look at the mesh settings, what NASTRAN does, it actually saves you a lot of headache, because it does a lot of work for you going into a lot of these utilities. And the mesh settings is one of those examples. When I launch that utility, it's already calculated an element size, 0.186. So it's already pre-measured and pre-analyzed my model and said 0.186 seems to be kind of a best fit mesh size based on the size of your component, or the size of your design, or the footprint of your design. Of course, you can tweak that. If I come up here and say, well, let's just make it 0.25, that's more of a coarse mesh, and that can impact your analysis times greatly. The more coarse a mesh is, the faster an analysis will run. The more fine it is, the longer it will take to run. Many times you can go to a very coarse mesh just to make sure you've got your constraints and your forces correct. See if it's bending the way you think it should. See if it's twisting the way you think it should. If you go to a really coarse mesh, say, if I come up here to 0.5, if I run the analysis at this mesh level, I'm probably not going to pay attention to the numbers. I'm not going to look at the von Mises or the safety factor or the amount of deformation. I'm just going to look to see, is the stress where I think it should be, and is it moving the way I think it should? If all of that kind of jives out, then I'll come back in here and I'll tweak my mesh settings and take it to a more fine level. That'll help me get more accurate results. So it calculated 0.18, so I'll just say 0.2. I'll adjust it just the tiniest little bit. Go ahead and generate that mesh, take a look at it and see what it looks like. So once you get the mesh or the net created, the one thing you're looking for is any kind of obscure pattern change. If you see something like that, that's a red flag that there may be a problem in that area. This typically will not happen on a natively created Inventor model. When you come from Inventor, go into NASTRAN dealing with those native surfaces, 99% of the time, everything is going to be pretty well intact. There's not going to be any kind of weird areas in the surface topology. However, if you've downloaded some components from Granger or McMaster-Carr, However, those components, the exports were generated, can severely affect their surface topology. You go and download a step file or an IGES file or an SAT file. When it translates into Inventor, the surfaces could have gaps. There could be surface deviations. For that matter, it may never have been a natively modeled file, and it could have been generated from a 3D scan. If it's a 3D scan, there's going to be all kinds of fun going on that surface. So this is what you're looking for, especially on imported or translated components. Looking at this particular pattern, everything is pretty well uniform. It's following kind of a unique pattern on that surface. You change to a different surface, the pattern changes slightly, but they're all still similar size, similar configuration. That looks good. When you get into a smaller area, like going around a bolt hole, I expect the pattern to shift a little bit. That still looks good. There's nothing jumping out here that says something's wrong with this mesh. Everything looks good and clean. Once you have material, constraints, loads, and the mesh generated, then you can actually run your analysis results. You'll notice that the analysis time for NASTRAN is pretty quick. It gives you a status report on the left-hand side of the screen on the NASTRAN output tab, and it gives you a flag box that says, hey, the solution has completed. Once you acknowledge that, it shifts you over and automatically displays the von Mises. Now, this is just the default setting. Von Mises is kind of the general best average of the principal stresses averaged together. It's a good generalized picture of the stresses going on in that model. But what does the color map really mean? If we look at this closely, we can see, okay, according to von Mises stress, we're experiencing a max stress of about 11,000 psi. And it flags where that max location is. It also flags where the minimum stresses are. Red is not always bad. Red simply indicates the maximum condition for that test. What indicates whether or not this is bad is you have to know the numbers. You have to know, okay, where is the stress yield for aluminum 1100? Where is that number at? Is it 20,000, 30, 40, 50? Once you know that, you have a better picture of where you stand on this stress. So if aluminum 1100 has a yield of 50,000, then we're good. We're at 1/5 of that yield. So we're not approaching this thing breaking or anything like that. And that's one thing that a lot of people misunderstand, is they think the red indicates the break or the fracture location, and it does not. It is simply the location of the max condition for that particular result. So if I switch over here and I look at displacement, you'll notice that the color map will change. So what's red in here indicates maximum stress. If I switch over to displacement, now the red's going to shift and it's going to go down to the other corner, and that's going to be the maximum movement or the maximum travel. So again, that red is not a constant that says this is a bad area. It's simply telling you this is where the max condition is for this result. So looking at this, we're moving about 7/1000ths of an inch. Not really a lot, and that's about what I would expect with 100 pounds and 200 pounds on the loading situation. Looking at the safety factor, that can be another good indicator of, are we violating the safety factor anywhere? We've got some areas in here that are a little bit of a concern, maybe just because of the different types of properties of that aluminum 1100. So we may want to tweak our material a little bit, or maybe go in and tweak our numbers to better match what we're actually using out in the shop. What you have in the shop could be a little bit stronger. It could also be a little bit weaker. And that's where getting the computer materials and the shop materials matching up can really make or break your analysis. So looking at this, von Mises says 11,000 psi on the stress. That's not bad. Very minimal displacement. Safety factor, all in all, safety factor looks pretty good. There's some areas in here that I could probably ignore just because I might have set it up incorrectly a little bit. But all in all, I would say this will hold for the conditions that we have. Now, what if we need to change material? We've already set all of this up. We've already run all of this. Does that mean we have to wipe it out and start over? No. Material change is pretty straightforward. Maybe aluminum is running a little bit expensive nowadays. What if we switch over to a mild steel? Will that gain us anything, or will we lose? You simply go back to your idealization, edit your solid, and change to that other alternate material. Once you do that, you can rerun. Everything stays the same. Your constraints, your loading condition, your mesh size, all of that remains constant just by changing the material, because we're staying in the same analysis. Now, if I want, I can make another analysis. I can duplicate this one in the tree. So I would have analysis 1 made out of aluminum, analysis 2 made out of a mild steel, analysis 3 out of whatever other material. You can have as many analyses in your tree as you want. And you can only run results for one analysis at a time. So if you've got 10 different analyses down in this tree, it's only going to run the calculation for that one analysis that you have active, not for all 10 at once. That would be overkill. So now changing this to a mild steel, the stresses, they changed a tiny little bit. We're still in the 11,000 range, still the same basic location for that stress. Looking at the displacement value, now we're moving about 0.02 of an inch. So we're not moving as much. So of course we did improve. Looking at the safety factor, it changed a little bit. Let's come back to the von Mises and let's zero in on some of the areas of stress. So if I come around and look, it looks like the forks have the highest level of stress, and it looks like it's out here on this front location. That could or could not be accurate. There's a lot of things that can tweak that and change that. First and foremost, I'm currently running with a mesh that is, what did I say, 0.2. The original calculation was 0.18. Okay, well, let's tweak it down just a little bit. Let's go 0.15. So a little bit below what the software originally calculated. So when I generate this mesh, again, I don't expect any meshing issues, but I will always kind of eyeball it, take an eagle eye approach, look around, make sure nothing jumps out at me as a problem with the meshing. Everything looks good, just got a little bit finer of a mesh. So now I can rerun those results, and that stress may move or it may change magnitude a little bit. And if it does, I can zero in on that even more. So right now we went from 11,500 and we jumped up to 12,200 PSI. So we did increase the stress just by refining the mesh down a little bit. And it still looks in the same basic location. There's a little bit wider spread of that stress, but it's still the same basic area. So we're getting more confidence that this is the area that's going to be a problem. We may want to beef this up or possibly change the design a little bit. But still, so far, we've only run 2 tests, and 2 tests are not enough to get confidence in the design. What you want to see is, as you change different things, as you refine the mesh, as you do local mesh control, you want to see the von Mises of test 1 to test 2 to test 3 to test 4 to test 5. You want to see that change be minimal. And you can even plot that out to say from test 1 to test 2, from 2 to 3, 3 to 4, however many you do, you want to see it change less than X percentage. Kind of I'll say the hip pocket standard is a 10% or less change between tests. Once you get 10% or less, you're pretty well confident that, hey, we've got a good mesh, we've got good properties, we've got good setup, things aren't getting really whacked out of control here. So this is probably where we're seeing the stress. This is probably the amount we're seeing within a certain level of confidence. And some corporations even say, let's go finer and do a 5% change. But kind of the ballpark that everybody at least shoots for is a 10% change. Once you get to that 10% or less, you've got convergence of the results. So looking at these results, okay, I'm not going to refine that mesh. I'm not going to refine that global mesh more than this, because the smaller I take this, the longer it takes to run. So instead of doing something like that, I'll probably invoke a local mesh control to zero in on what's going on. We have that ability with NASTRAN to either select vertexes or surfaces. And let's say I want to refine the mesh for all of these particular faces here. I want to see where that stress is. So I'm going to select quite a few of these faces, and I'm going to adjust the size. Now, typically on a local mesh control, it's a good ballpark to take your global size and cut it in half for a local mesh control. You don't have to stick to that, but it's a good starting point. So I'll just say 0.07 for the mesh refinement. So go ahead and generate the mesh, and you'll notice the mesh in and around and connecting to those areas will get smaller and adjust to fit it. So any surfaces that contact the surfaces being refined, that surface will have mesh adjustment along that contacting vector or along that contacting edge. So the global mesh automatically adjusts to incorporate that local control. Let's see if that changed anything. Simply rerunning the analysis results, and we'll see if that goes. We started out at 11,200, we jumped up to 12,200. The location was pretty well in the same general area. Okay, now we have jumped to 14,300. That's a pretty significant jump. So we might have to do continued refinement on this. But we are seeing that that stress is staying in that same basic location. Further refinements we might make is we might tweak down the global mesh a little bit more, might tweak down the local mesh control even more, just again to kind of zero in and see where it's going. Once you have your results, you can generate a report from NASTRAN. And when you try to generate the report, it may flag you with a box that certain parameters have to be turned on, which is fine because you can just tell it here, go ahead and turn them on. Once that's done, then we can come back, we can generate the report, and it will generate, well, it's going to present a dialog box to allow you to input certain options. You got all the optional information relative to the test you're running, the date, who ran the test, what it pertains to. Then as you dial through the screens, you're able to input summary information, make assumption statements, look at any kind of definitions you want to set in, any kind of contacts that were defined if we're dealing with an assembly situation, the type of mesh and how many elements we're dealing with, any structural loading situations, supports, and any kind of summary information for the solution. You can enter all of this information in, and it will generate an HTML that can be shared out within the company intranet. So when I finish this, go ahead and save that, and it goes through and it runs through each one of the result plots. So it's grabbing a von Mises screenshot, it's grabbing a displacement screenshot, safety factor, and a deformed screenshot. Loading up the report, everybody can see this. Nobody needs any kind of special software to look at this. From the lowest employee to the highest executive, they can all pull up this HTML, dial through it, look at the summary, look at some of the model setup, the definition, material properties. You've got this on record now in case you guys find out, hey, the shop material is a little bit different. You can come back and say, okay, yeah, we need to rerun this report because it's grossly incorrect. Looking at the mesh, how the mesh was defined, then you actually get down into some of the loading situations and the solution plots so everybody can access that information. At this point, this is a piece part. And you're not limited to just piece part analyses. So if I close this out, bring up an assembly, and in this particular case, this assembly is actually cut in half because, again, you can do symmetric loading and constraint conditions and situations. But for this, I'm actually going to take off that cut so that we can deal with the overall lever and the pins. So when I come back into NASTRAN, it's the same process flow. We're dealing with a linear static type of analysis. Looking at our materials, we're going to tweak the materials for each one of these. This is the cast lever we're working with. It's going to be made out of mild steel. And then on the pins, we're going to make those out of an alloy steel. So I will simply reference those from the Autodesk library and associate that to each one of the pins. And leave that color, that's fine. Constraint situations, same thing. We're going to constrain and fix the pins to where they are not going to move. They're going to hold this lever in place. Tweak the graphics so we can see it a little bit better. And I missed the bottom one, so let's do that one as well. Actually, we're not going to constrain that one. I'll leave that one open. The loading situation, similar as before. It's going to be a negative Z load of 200. Total force on those. Adjusting color preferences and previewing. And then another loading condition on the bottom pin. This one is going to be in the negative Y of 100. Tweaking it and make sure we've got the correct direction. We do, everything looks good. Now we get into the situation of contacts. So when you're dealing with an assembly, contacts will determine whether a component can move and how it can move relative to another component. And the nice thing about NASTRAN is it has an automatic contact solver. You can run the auto mode and it will look for contacts between those components, and your analysis settings actually tells it which contact type to use. So it says, okay, use a bonded contact if the surfaces of two components are within basically 0.004 of an inch. If they have 0.004 or less of a gap between those faces, it applies that bonded contact. If the gap is bigger than that, no contact is generated. So you can generate that contact manually. The different types of contacts you have, a separation contact, a bonded contact, which basically represents a welded type contact. You also have sliding contacts that have no separation between the surfaces, separation of the surfaces, but no sliding across their vectors. So various types of contacts and controls for those situations. Also, if you determine, well, it found these contacts, so there's one down there, there's another one for the other side of the bolt hole, and then here's this one at the base. Maybe we're going to change this one because it made all three of them bonded. But on the third one, I'm going to tweak that one and say, well, let's just make this one a sliding, no separation contact. So that's going to allow it to rotate around, but it's not going to allow it to translate in any of the directions. All right, so now looking at the mesh control again, just running with the global settings that the software calculated. The mesh looks good. I may want to come back and refine it a little later, of course, and then run the analysis. The analysis will take just a second or two longer because it is dealing with more components and a larger file set, but it is this same type of reporting mechanism as with a piece part. You still have access to the von Mises. Again, we're seeing similar results as what we saw before. We've incorporated more components, but the results are virtually the same, which means our piece part is probably good enough. We can probably just work with that and not worry about muddying up the water with more components. But sometimes more components can show you some outliers and some problems that the single piece part may not. So you got to kind of play the scale game back and forth with that to figure out which one works best. Looking at the displacement, we're 11,000 psi on the stress, and we're looking at about 1,000th of an inch for displacement. Safety factor violation, of course, it's calling out the pins, so I'm probably going to ignore that and look at the main cast lever for the safety factor calculations. The other thing is when you have an assembly, you can actually exclude components from the analysis. So they can be here in your assembly model to show the detail and for you to constrain around them and things of that nature. But you can also come over here and say, well, you know what? Let's take that large pin and let's exclude it from the analysis. What that does is it takes the math off of that pin. So now anything that happens in that area doesn't get calculated against the pin shape or the pin properties. and that can dramatically improve your analysis time. So that was the basics of start to finish for a NASTRAN simulation, and it's more or less a typical simulation. Many people are running a linear static simulation as a start to maybe running a nonlinear static or a buckling simulation next. This is kind of the groundwork to make sure you get all of your constraints and your loading right and make sure it's stressing the way that you think it's going to be stressing. So at this time, we'll go ahead and open it up for any questions. So Keith, how are we looking on the Q&A?
Looking pretty barren. There's no questions that have been posted.
Okay. We'll give another minute or two. If you get into a situation where you're not sure what product you need, because we talked about multiple products early on, we talked about NASTRAN, we talked about simulation CFD, we talked about robot structural analysis, and I did not even mention Inventor Pro FEA. There's a lot of situations where we'll run Inventor Pro FEA because it's a little bit faster. It yields the same results as NASTRAN, but at least Inventor Pro is a good, quick sanity check of, are the constraints where they should be? Are the loading situations where they should be? Once we get that tweaked, then we can go to the next step, launch into NASTRAN, and improve upon that analysis by tweaking the mesh down more, getting local mesh control, changing the material a little bit, maybe running more iterations, or even going into a nonlinear analysis or a linear buckling analysis. So Inventor Pro is actually a good place to start, just to iron out some of the details of the setup, because it's a little bit faster than NASTRAN. But if you get into those situations and you're not sure which product you need, give us a call. We do have technical staff experienced in all of those products. We can help you iron out the details of, well, maybe you need this one, and maybe you need a combo. You could be in one of those unique situations where you need NASTRAN and simulation CFD.
So, Kendra, one question came up regarding the material assignments within Inventor. Do those have any effect on the NASTRAN materials?
The material assignments you create, typically you're going to have those materials added to either the Autodesk library or the Inventor library, especially if you're going to be using that material across multiple IPT files. It's going to make life easier if you put it in a library. Whatever material you have assigned in Inventor, that material carries over, whether it's generic or it's a customized material. So the properties assigned to that material carry into NASTRAN. You could be in a situation where, well, maybe you didn't fill out all of the Inventor properties, you left a couple of them blank. In those cases, many times NASTRAN will flag you and say, I can't assign this material because that particular field, like if you left Young's modulus blank, okay, that's not going to work. You're going to have to put something in there for that material. There are other material properties that it can actually calculate based on the situation. So it's a little bit give and take. But if NASTRAN needs something from you, it's going to tell you.
Another question that came up was the convergence features. And basically, there are a number of methods that you can use to find convergence on the mesh. That might be something that might be better to table with a specific solution engineer.
I would agree on convergence. A lot of times it falls back to the situation you're working with. Many convergence, if you go with a generic convergence, then that's simply running test to test to test to test to see if the results change enough or not enough. And you can get good convergence confidence there. But then when you get into certain unique situations, that will likely not be enough and will require further settings and further tweaks to get that convergence. I would say in those situations, give us a call. Let us get one-on-one with you and an engineer to iron out the details of what path you need to take. As user-friendly as Autodesk has made simulation overall, they've made the ability to go in there and create a simulation and run a simulation and look at the results of that simulation. They have made it very user-friendly and very simplistic. There are a lot of, I will say, background settings and background knowledge and background setup that you need to have, and that's one area that we can try to help you with. Any others?
As far as a guideline for your starting mesh size, there's a couple of obvious caveats to that you typically want to try to encompass. For starters, we want to make sure that your element size is at least equal to your thinnest section of the component. We want to make sure that we're not creating a really large deviation in the mesh element sizes. Ideally you're trying to create equilateral tetrahedrons or equilateral sized triangular pyramids, and in order to do that effectively, sometimes that requires you to shrink the mesh size down or create mesh quality controls in specific areas where you specify what that size is. With that being said, is there a specific guideline for, every single model? No. What we're really watching for is, is the mesh itself uniform without large amounts of deviation? And in one of the solves that Kendra actually ran, you could see there were some warnings that came up during the engine solve. Where it was basically saying, there are elements in here that are beyond the limits of what you've specified as, quality definitions for your mesh.
Right.
And so obviously with that in mind, you just got to pay attention to the warnings and look at the mesh and investigate the mesh per model. But that's definitely something that we walk through during the training class. As far as what's a good mesh, how do you add mesh controls, how do you deal with these specific types of warnings or errors that can occur.
And that brings up another good point. I made the comment about when you switch over to a nonlinear static analysis, one of the options you have control over is whether or not large displacements are analyzed or calculated. And one question that comes up is, okay, how much is a large displacement? Is it 1 inch to 3 inches or 5 inches and above? And the answer is it's all relative to the situation. So a large displacement on a 12-foot long, 10-foot wide I-beam might be a foot, whereas large displacement on a 12-foot long 2x4 might be 1 inch. So it's different on every situation. So there's no, and you get into that a lot with various FEA packages. There's no global standard or blanket answer for some of this. It's going to be unique to that situation. And that mesh size can be one of those. The software does a good job at calculating based on that minimum material thickness, but then again, there could be little outliers in there that, for whatever reason, the algorithm didn't find it. So the mesh in that area of that small material thickness violates our mesh control settings. So that's where the errors come up.
One last question here before we call it. Kendra had mentioned working with imported models. If the models are coming in intact, they're solid, they don't have any warnings or errors on the import, they'll work just fine in the FEA environment. What sometimes happens is, like, if you were to say import a STL file, for example, the STL file is most likely not going to be solid to start from. And so you would have to do work on it in order to make it functionally solid. before you could really use it in the tool. With that being said, the software, the NASTRAN tool does allow for, non-solid objects to be worked with, right? So I could, in fact, make a surface model and use it for, say, sheet metal componentry. I don't necessarily have to have a solid. And we cover all of that process. During our 2-day NASTRAN new user course. So it would cover a lot of what Kendra talked about today, as far as meshing and defining your constraints, your contacts, your loads, the different types of simulations that we can solve. Working with the materials, and obviously expanding upon all of that into nonlinear and vibration analysis, and even some thermal stuff. So if you do have an interest in learning more of this process, definitely reach out and sign up for a NASTRAN course. There's a lot to learn.
And that course is something that we run semi-routinely. We may not necessarily have a class every month, but we definitely run, I say we average one NASTRAN class per quarter. All right, and with that, I want to say thank you everyone for attending. If you have any other questions, you can definitely submit them and we will take them offline.